A quick note before we begin today. Due to some equipment failure, the first 15 minutes of this episode sound worse than you would normally expect from our show. We think the episode's great and still worth bringing to you, and it gets better later. But as you'll hear, it's not your headphones, it's us.
Yannick, welcome to Validated again.
Thank you. Excited to be here.
Yeah. So we last talked probably over a year ago at this point, which is pretty heavily focused on what you guys were building. We'll get into that a little bit later. But the main reason I wanted to have you on is it feels like we're sort of at a turning point with zero-knowledge systems. There was a huge amount of hype from 2018 kind of through 2022. It feels like we got a little quieter in the last few years, but a lot of stuff's actually launched and usable. And on Solana, zero knowledge has actually had a little bit of a resurgence. It's actually become a chain that has a ton of different ZK primitives, a lot of different companies building with zero knowledge technology, whether it's from state compression to privacy layers to confidential computing to all sorts of other types of applications. But at the same time, a lot of the big name zero knowledge players that bet big on the technology, bet big on L2s that we're going to be using it, have really struggled to sort of find differentiation and a reason for people to sort of care about what the technology is built on and how it actually works. So it's a whole bunch of stuff I want to talk through today, but sort of to start off, like give us a run through of like, at the end of the day, like how does zero knowledge technology actually work in practice?
Yeah, sure. So there's essentially you can think of zero knowledge technology as this big term with different kinds of technologies falling under that term. And there's zero knowledge proofs, which is the one big traditional way you're mostly referring to for zero knowledge technology, but there's also secure multi-party computation and fully homomorphic encryption. Those three basically form what we think of as zero knowledge technology. Now, the security and different properties that zero knowledge technology enables come from cryptography at the end of the day, right? So there's a lot of math, a lot of cool math, I have to say, and cryptography involved. But the history of ZK really is that in the 80s, the first kind of zero knowledge proofs have been designed. And back in the day, those were interactive proving protocols. So a zero knowledge proof usually involves two parties. Me in an example, the prover, and you, Austin, the verifier. And with a zero knowledge proof, I'm able to convince you of the truth of some statement without having to share the statement itself. Simply just communicating the validity and the truth of some expression. And back in the day, in the 80s, those were interactive protocols. So we had to perform some complex computation with each other to generate a proof. Over time, those have evolved into non-interactive proving schemes.
So 100% makes sense. Sort of and or but, right? We sort of have systems that do some version of this today, right? I can give you a installer from a closed source software provider, and it includes a certificate that I can verify that no one's monkeyed with the code without actually looking at the code myself, because I see this sort of certificate that's said, yes, the checksum matches, or you can publish a checksum somewhere, and I don't actually have to see the source code to verify that something is what it says it is. We have wallets that have public-private key encryption where I can verify that you have signed a transaction without having your private key. So how is this similar or different from a lot of these encryption methods we're familiar with today that are used to provide some amount of verifiability?
Yeah, so I think especially in the context of what you were referring to with some signed certificate for some software provided by a vendor, that is really a case of some trusted interaction, because at the end of the day, you're trusting someone that what at the end of the day this interaction expresses is that the source code is supplied by some entity, right? So you have this remaining trust of, okay, I trust this entity and I know that they've sent it to me. So it's sort of like an encrypted channel, if you will, right? Because they've signed the software, you can trust to install that software because you have a contract with their company, right? And if they were to exploit you, then you could sue them in court. So I think what's key, and that's something that we're trying to achieve with blockchains in general, with Solana, with what we're building, but any kind of distributed trusted systems, is removing single points of failure, removing trusted entities. So verifiable compute is an important aspect for that. And that's one of the properties that zero knowledge proofs and other cryptographic schemes can provide. So then the term zero knowledge proof can be a bit misleading, because a lot of usage of zero knowledge proofs actually circles around scalability and verifiable compute mostly. But there's different kinds of properties for a zero knowledge proof. One is the secondness of the expression. So that basically expresses that there's some asymmetry. There's someone generating the zero knowledge proof, the prover, and someone verifying it. And there's a computational and informational asymmetry between those two players. So you can express a very complex computation in a zero knowledge proof, which in the case of ZK snarks has this constant, always the same complexity of evaluating and verifying the zero knowledge proof. And that's where scalability comes to play. That's where ZK can be used as a scaling solution. Because you, at the end of the day, can outsource computation to some third party and simply verify it.
So I don't want to get too far into the math, because you're going to blow past me very quickly. But the concept of I am trying to verify something without knowing its contents, right? In the traditional world, the only way that's done is a third party vouches for it. So KYC is a great example, right? My accountant vouches that I am an accredited investor. I don't have to actually show you my bank statements. You trust him because of his accreditation. How are you able to, like, at a high level, prove the contents of something without revealing what that is?
So I think there's something that can blow your mind even more, right? So zero knowledge proofs, just generating this proof and submitting it to a third party. I would have to sort of go into the weeds of it, but I think as a concept it's easier to understand. So I have some secret and I can do some mathematical permutations, right, and submit a proof of the operations that I have performed, right? So you know the algorithm that I've executed, I know the algorithm that I've executed. So we both have this shared knowledge of the function that should be executed, the kind of permutation, right? The more disturbing concept, if you will, is what we are actually doing, and that involves not just me having secrets and running something, but instead allowing a network of nodes to run something over secrets. The network doesn't know those secrets, and they can generate a verifiable output, right? Which is even a more crazy concept if you think about it, right? So I think at the end of the day, this technology enables use cases that we haven't seen before. All of those three protocols enable new use cases in a distributed setting that make those systems way more resilient and performant at the same time.
Yeah, so I want to talk about some of the dynamics you mentioned around compute asymmetry. So most encryption methods we use nowadays, most security methods we use nowadays are effectively free to verify, right? Signature verifications on a Solana transaction is basically as short of a time as you can get it to be. Me validating a certificate is valid for a website or any other type of encryption, it's not a computationally intensive task to like encrypt my iMessages. So what is it about zero knowledge systems that, if you talk to folks about zero knowledge systems, it feels a little bit like nuclear fusion. Like, oh, it's always just a few years away from mass applicability. So what is it actually that requires what not from a math side, but what components of the system require compute, and why has that been such a barrier historically?
So one of the key problems really is that you're operating on a completely different computer, if you will. So if you run your normal signature verification, those algorithms usually are optimized for some binary operations that your computer can perform, right? And those can be parallelized.
There's hardware acceleration to support this kind of
and you're basically operating over numbers and bits with with zero knowledge proofs and all of that cryptography, where you want to represent some computation that a normal computer can operate in a cryptographic way, you need to transmute that into a different representation. And that representation involves so-called elliptic curves, different functions, and finite fields. And that makes things much more complex because computations now are being represented as so-called circuits, arithmetic circuits, for example, of which you can think similarly to fuses in an actual chip, right? It's actual circuits, it's signals, and it's not those signals from a computer, but instead it's finite field signals, if you will, that run in those fuses. So there's complexities involved in representing operations that on a normal hardware are efficient in this virtual circuit format. So that's really one of those problems why there's significant overhead associated. And there's hardware acceleration for those things as well, but it takes time, I guess.
Yeah, I guess that was sort of the scale problem feels like it should be more solvable than it seems to be. Like between FPGAs and between like the way, like you look at something like ASIC acceleration in Bitcoin, and that sort of revolutionized what was possible in terms of hash rate there. It's not like the Bitcoin folks had crazy super corporations organizing venture rounds to build ASICs. I mean, some did eventually, but with the amount of money that's gone into ZK research over the years and the amount of money that's gone into funding ZK crypto companies, like, why is it today that we either don't have hardware that's capable of doing these things? Like, how much of the breakdown is like research versus like no one's actually just built it yet?
That's an excellent question. I think it goes into the direction of why we at Arcium initially were working with zero knowledge proofs, right? Back in the day, we were called elusive, and we were doing on-chain privacy with zero knowledge proofs. But eventually, we pivoted, and I would rather call it evolved into using secure multi-party computation instead. Because for us, it was some limitation that could not be overcome that's associated with ZK. And what we've noticed, I think, is that there's quite a lot of teams that also came across those limitations. And especially on the confidentiality and encryption front, there's just this big limitation of you just being able to provide privacy for one party that interacts in this prover verifier system. But you're not able to build smart contract systems. You're not able to aggregate data. And so that's one of those big limitations that we came across. And that's why we decided to go down a different cryptographic road.
Yeah. So talk to me a little bit about how that new system works and how it differs from some of the other zero knowledge technologies we've been talking about.
So MPZ, as similarly to ZK, has actually, they have evolved in a parallel fashion, basically, also starting in the 80s. I think the fascinating thing about MPZ really is that it allows a set of participants to jointly compute a function without having to share their individual inputs. And MPZ in our space mostly gets associated with some key signer wallet management, right?
Right. I'm breaking my wallet into a few pieces, and then multiple compute puts it together to sign a transaction.
But MPZ really, at its core, allows a set of nodes to jointly run a predefined function, an algorithm, and have individual inputs and keep those inputs private while producing a shared output. And what we're essentially making use of also with the research that we're doing is with new trust models that have become possible with those kind of systems. Because initially it was really only honest majority, which I guess you're familiar with, right? But for the folks listening, most Byzantine fault tolerance, practical Byzantine fault tolerance systems have this honest majority as trust assumption, right? So you have some qualified majority that has to behave honestly, has to behave according to protocol. We've seen a breakthrough in those kinds of protocols that now allows for dishonest majority, which basically inverts it. Only one single honest participant required to guarantee different properties for those computations.
So I think it's worth diving a little bit more into how that works, because like blockchain is always, and most of these systems have always had like an objective truth problem, right? Where it's like, unless you're like fairly Catholic, like objective truth is pretty unknowable, right? In the sense of like you need an external reference point to base something as being true, which is where the honest majority assumption comes from. That you can only like it's the whole thing about like, Ethereum Classic is actually the real Ethereum, right? And like the thing we all call Ethereum is actually a fork, right, of Ethereum. But we all have socially decided that this is the main one, the other one's Classic. But like from the computer's perspective, there's no way to know which one is quote unquote real Ethereum.
Yeah, I think that's actually an excellent question, and most people don't ask me that question. So it's I think even the smart question to ask, right? Because how could dishonest majority function, right? As a concept, because how could just this one person be correct, right? If there's only one honest participant. So that's also where the connection between Arcium and Solana comes into play, actually. Because what we're saying essentially is Arcium is a purely computational network that supplies computing capabilities that Solana itself cannot facilitate. Confidential computing, generalized confidential computing, basically. And so we make use of this connection with Solana. So we have a program on Solana that functions basically as entry point, as mempool for computations happening within Arcium. And so Solana sort of becomes this truth layer, if you will, where there's just the consensus over what computation should be performed. And so if Arcium, within Arcium, a computational cluster, doesn't run a computation as it's tasked to do on Solana, the corresponding party within the cluster, it could be all of those nodes or just one or 0 nodes, right? If anything goes wrong, anything doesn't go according to protocol, they get punished for that. So that's really where this connection comes into play, and where actually blockchain forms a system that can overcome limitations from very theoretical papers. Because now with Solana, it becomes possible to overcome problems that have always existed within those papers.
Yeah, that's fascinating, because there's this like trend right now, which is like, oh, anything that is built on top of something should probably become its own L1, or at least think about it, right? And that usually all you're getting is some form of like economic security or network effect or something along those lines. But this is like a real case where the security model would be worse if it didn't have a blockchain underneath it.
Exactly. Yeah. And it wouldn't make any logical sense to then also extend it into an L2 infrastructure, I think. I really feel like this setup will be the future, to have this big consensus mechanism, and then have Arcium with this honest majority, which can perform specific kind of executions in an asynchronous way, but doesn't have to find consensus over state.
Yeah, that's really interesting. So what from a like a practical tools perspective, what does this allow folks to do either on or off blockchain that they really can't do today?
So
without using the term healthcare records.
Yeah. So it's funny because I think Breakpoint has shown me and my entire team that basically everyone craves some form of confidential computing within their applications.
Yeah.
So I think that's also one of the big problems why all of those CK infrastructures haven't so far succeeded, is that they force developers to learn some new paradigms, learn some new technology, actually need to learn what a circuit is and all those kinds of things. We, for example, abstract all of that away from developers. So we just say, you want confidentiality as a developer, so all you have to do is you mark the functions and the state within your program that should be confidential as confidential.
Yeah.
And then you let Arcium process that and settle that back for you, right? So that's what we're trying to achieve. And so what folks can have is they can have any arbitrary Rust program essentially be executed in a confidential way. And so there's very tangible use cases. I think one straightforward use case, and has been amazing to see folks on Solana start building that with us in our private testnet. Private markets, right? So dark pools, for example, since 30 to 40% of daily US spot volume happens in dark pools, right? And so there needs to be an answer for that on the blockchain as well. A lot of folks I talk with from the TradFi space actually often say, JP Morgan is actually running a private ledger, right?
Yes.
But they can't move to some public ledger because of confidentiality concerns. So I think that will be a significant step also in regards to stablecoin payments to further enhance the adoption. And that's something where we are closely working together with core folks in the Solana space. Because Solana has the confidential token program, which
it's only for transfers.
Exactly,
you can't run a market on it.
Exactly, has some limitations, right? And so by extending that to allow smart contracts programs to have confidential balances, have confidential interactions between parties, that makes it so powerful. Then that will allow some confidential lending protocol, right? And will allow for some form of unified liquidity for all those folks to build applications with that. But I think DeFi is only the first part. We've seen a lot of folks in DePIN as well be very interested in this kind of technology. So that ranges from people just wanting to replace some trusted server infrastructure with something trustless. That is being executed on the blockchain. So, for example, have some proprietary algorithm that does perform some action within a DePIN. Have that be executed now in a verifiable and trustless way together with their program. And on the more complex side of things, I think data aggregation and also federated learning and machine learning is something. And my take on AI x crypto has mostly been that I think AI agents sort of are glorified bots, and most of it is fully artificial, which makes sense, I guess, but it's just this superficial forced marriage. But I think confidential computing can actually be a logical fit because we have very highly sensitive data that could benefit all of us, could benefit humanity as a whole, if we would find a way to safely aggregate that into models and then have a way to, for example, monetize this data, right? So it could be encrypted sensitive data that's collected on your phone by some DePIN project, for example, that then uses decentralized confidential computing to train a model that in itself remains encrypted. So it's stored on the blockchain as an encrypted model. And so whoever wants to use that model has to pay some smart contract, which then distributes those funds back to the people who gave their data to the model. They actually never had to give it, right? It remains their ownership, but they provided encrypted data that formed that model. So there can be new economic incentives to produce more high quality data. And I think down the line then, what that will lead to is a utopian future where there's safe AGI that runs on Solana, for example, right? Because you can have safe access control and the most high quality data being encrypted. So I think that's something where blockchain can actually enhance AI, I think,
Yeah, the dark pools piece you talked about is really interesting because there's a lot of stuff in this space that feels like it's transparency first.
Yes.
Right?
Yeah.
And there are a lot of situations where transparency isn't necessarily useful or necessary for a market to function. I guess, I think a lot about OTC desks, right? How they're a huge percentage of volume and there's literally zero I mean, you can see the movement on chain, but like other than that, like it's all settled in wire transfers after the fact, and you can't really see where price is moving on those sorts of things. Is this technology fast enough today that you can really run like a central limit order book in a confidential compute environment? Or are we really still talking more like maker and taker, like OTC style systems?
So there's different approaches. And what we've seen is teams, for example, using FHE, fully homomorphic encryption, attempting to do that. And that's not a market with sufficient throughput. But that's one of the reasons why we decided to use secure multi-party computation. Because that yields fast performance. Now, moving from an honest majority to a dishonest majority trust assumption makes things a bit slower because you want to operate in the smallest possible trust assumption, right?
Right.
So what we are using is a so-called MPC protocol in the pre-processing model, which means that when you have a computation, order matching, for example, that computation is now split into two phases. One pre-processing phase and one online phase. And the pre-processing phase is independent of the actual data being used, so the encrypted orders and parties, whatever, and actually even the function. It just is used to generate so-called correlated randomness. And that correlated randomness is then being consumed in the second phase, the online phase. And in the online phase, then operations can be performed way more efficient because we have had this pre-processing. So one answer to the question, I think, would be, okay, since we're using the setup, we just need to ensure pre-processing takes care, has happened. Then we are able to facilitate almost as fast as plain text operation times for the online phase. What we can also do is we can make use of oblivious data structure, oblivious sorting mechanisms, where we can then asynchronously sort large order books and crank up the speed that way. And then there's, I think, I would say that performance-wise, we're at a point where it becomes feasible. Basically, I see my task and the task of my team and our researchers at Arcium to just similarly to what the fire dancer team is doing, but doing it for MPC, to just make that as fast as possible, come up with new cryptographic protocols to batch together communication, make use of hardware acceleration, make use of different elliptic curve operations we've been tinkering with. So
So I wanna get into a little bit of the differences between fully homomorphic encryption and MPC for sort of these use cases. So there's sort of like, you can think about it as like, what components do we care about being private, right? So there's like the first version we talked about that's like software encryption, where it's like, I trust you and you want to make sure I can verify that what you've sent me actually arrived, right? And no one like monkeyed with it in the middle. There's the stuff you've been talking about too, where it's like, oh, we need to verify that like something exists without proving what it is, right? That's kind of one piece we've talked about. And then like FHE, the way folks talk about it is like, oh, a computer can compute a result without knowing the inputs or the output of that result, which is like, we've had black box style computing for a while, but usually the inputs are known and the outputs are known. And that process in the middle may be like semi-black boxed. But like, how do these, first off, is that a decent like explanation of how this stuff works, or like from how you would interact with it perspective? And then where does MPC versus FHE sort of have different advantages and disadvantages?
So I think this idea of black box computing really describes what both MPC and FHE are trying to achieve, and but also trusted execution environments are trying to achieve, right? So if we're really talking about confidential computing and black box operations, those are the three technologies to think about, because CK allows for verifiability
Yeah.
and one-party privacy, basically, right? So those three, FHE, MPC, and TEEs, are what we should compare. TEEs is for me, at least from me being able to look at Wikipedia and at news articles and different software exploits, just isn't the way to go.
Yeah, it seems like SGX is hacked every other week, pretty much.
Yeah, exactly.
And also, if you don't have physical security on the machines, it seems like it doesn't particularly work.
Yeah, I think it works in a trusted cloud environment, with a trusted software vendor, right?
Right, with physical security.
Exactly, yeah.
Yeah.
And that's also so striking when Apple announced their TE hardware for Apple Intelligence. In their blog article, they were describing them physically guarding the machines exiting the manufacturing plant and going to the data center, and you just have this mental picture in mind of someone with an assault rifle guarding a computer, right? And you're like, is it actually this amazing hardware that can do black box operations? Doesn't seem that way, right? So it sort of feels like it being impossible. And to be honest, we also have to look at cryptography in a critical way and have to think about quantum resistance, right? So I think that's also something that a lot of folks, especially in our CK, MPC, FHE space, try to ignore. But I think that's something that we need to work on with faster pace as well. But I think TE is basically, and for the folks who are not as familiar as Austin and I are with that, hardware-based security, where basically the hardware manufacturer has some privacy and security promises that they give to whoever purchases this hardware. And we've just seen this huge amount of exploits over the years. A few weeks ago, I think the most recent one with Intel SGX, Intel's trusted hardware.
For like the third time.
Yeah. And we even had blockchain networks completely rely on that, and their privacy completely get researchers were able to completely decrypt the secret network back to the Genesis block. Which is crazy. And the Avalanche bridges and a bunch of stuff like that. Yeah. And so I think if you want to build this technology that is future-proof, right? To build this open network on which the NASDAQ can run, right? You don't want some technology where every 5 years you need to replace it with a new trusted system by some other manufacturer. You want something future-proof. So purely cryptographic systems, I think, is the answer. And then the question is FHE versus MPC. So FHE basically, as you described, allows you to have an encrypted representation of some value and perform an operation on that encrypted representation of a value and remain in that representation, right? So it's you're not exiting, you're not decrypting, you remain in this encrypted representation, which is incredibly powerful. Yeah.
It's also very hard to think through how that, like, we don't have a model for that in the physical world. Usually there's it's a black box, like something happens inside the box. It's very hard to think of anything else where I can perform an operation on something and I have no ability to see what the thing is. It's very interesting.
That's true, actually. Yeah. But with FHE, powerful concept, and the problem really is its practical limitations, and that boils down to some of the operations that you're performing with FHE, fully homomorphic encryption, homomorphisms, mathematical homomorphisms, basically means that two operations are homomorphic, which allows you to remain in this representation, and multiplications, as being one of those operations, are costly because for when performing those multiplications, so-called noise is being accumulated. Right. And once there's too much noise accumulated, it's not possible to use that ciphertext anymore. So this noise needs to be reduced using costly bootstrapping operations. And that's mainly what makes FHE so incredibly costly, meaning in practice, many orders of magnitude above your normal execution times for whatever operations you need to perform. And that's, of course, not just some latency penalty, that's also computational power overhead, right? That you have to work with. So that's why we're using MPC. Now, MPC is very closely related to FHE. And so what we're using is not fully homomorphic encryption, but somewhat homomorphic encryption, which is a subset and just makes use of one operation being homomorphic, and multiplication is this very expensive operation. We are able to make use of actually what we discussed earlier, this pre-processing.
Right.
We can make use of that, and that just makes it very, very efficient.
Yep.
But of course, there's more trade-offs you have to think about, right? So with FHE, you're in this encrypted representation, which is nice. But what if you want to exit that, right? What if at some point under a given condition you want to selectively disclose some information about the encrypted state, which especially becomes important on a blockchain, because I think you don't want everything to be encrypted. I think you want to be able to move in and out of those representations.
Right, or even just like you can see there being needs to checkpoint stuff and to provide some amount of external observability at like various pipeline points.
Yes. Yeah, I think so too. And so that's something that MPC natively allows for, this form of selective disclosure. So I feel like, and luckily I'm not alone in with that opinion, but I mean, we have one of the leading FHE researchers in our team, and he's also fully convinced of MPC being this technology that allows for this generalized confidential computing, both for on-chain applications, but also for off-chain applications for AI use cases. So I think that's the correct path to take, and to make use of any kind of hardware optimization that we can make use of, both for MPC, but also FHE and CK.
Yeah. So changing topic a little bit, you're a co-founder.
Yes.
You guys do a lot of low-level research on this type of work. Everything we've talked about today is about as far away from a commercial product as you can think of. How do you think about balancing when you're working at this type of like fairly groundbreaking technology, and a lot of it being math, right? There's no moat around math. You publish the paper, it's out, everyone will use it, right? Yeah. How do you think about building a product and a business around this type of like low-level research?
So I think it's really important to have a team that can satisfy both ends of what's required to build a product. It's this low-level research, being able to do the mathematics, but at the same time, as we discussed earlier, be able to build programming interfaces that developers can just use. Right?
Yeah.
It doesn't make any sense to build the best cryptography and then hand a research paper to the developer and be like, okay, read this manual, read this research paper, and then afterwards you'll be able to add confidentiality.
Right.
And so what we're working on really is to have this most accessible kind of confidential computing, because otherwise, why would anybody use it, right? So I think that's important, striking this balance. And to be honest, those low-level researchers and PhDs often tend to not find the most practical things, and so it's important to have also folks who've including us when we were building Elusive, but now in the meantime have more folks from the Solana ecosystem be part of our team who then think like a developer, right?
Yeah.
They think like the end user. And so I think in general, building a business around this for us means building Arcium as a global supercomputer, and allowing anyone to access that supercomputer for confidential computations. And the supercomputer just needs to be as accessible as possible, because then any kind of application can have confidential computing.
Nice. And what do you see as sort of technologies that are worth paying attention to over the next few years within this domain? It feels like every few years there's a new classification of something that gets stuck on people's minds, raises a bunch of money. Maybe it works, maybe it doesn't. But what are you looking out as sort of some of the advances coming to either MPC or ZK technology in general?
That's a very good question.
Or do we kind of have it? We just need to make it faster.
So we have a lot of what we need, actually. I think so too. And it's not just about making it faster. It's also about building those things. And as I said, making them accessible. I think that's one of the big problems with ZK, I think. Also, what's not accessible is requiring developers to learn a new DSL. Mm-hmm. That's also not accessible. And we've seen ZK teams that now introduce a new domain-specific language that developers need to learn. I think that's one of the superior approaches that Solana has taken as well, to by default say, hey, developer, use Rust, which is this general programming language, which over the time that Solana adopted it, has been adopted by so many people in parallel, right? So I think that was one of the most logical decisions to be made. And we are trying to do it in the same way, to allow developers to add confidentiality where they're at right now. But that takes time. Tooling takes time. And optimization takes time as well. So be it hardware acceleration, be it communication optimization, be it optimizing network communication protocols. There's just a lot of things that need to be optimized. I think what I personally would be or am most excited about really is protocols that optimize network communication. I think because that's one of the big bottlenecks, optimizing network communication. And the biggest thing for me is oblivious data structures, because what my vision really is, and that might not be super relevant for blockchain applications, I guess, but my vision really is to allow for fully encrypted RAM programs. So it's not just some small functionality, but it's anything your computer can execute. And it's not like you pay gas for the computation and then it's done, but it's run for the next 10 years in a confidential way, right? That's and that requires complex sort of encrypted data structures that can have arbitrary size. And so, I think that's what I am most excited about in that space.
Excellent. Well, Yannick, thank you for coming on Validated.
Thanks for having me.
Appreciate it.